start recording now. Okay. So,
Professor?
yes.
I can't find the PDF. It's not in the course stream.
It's not under files?
It is under files.
It's like the first file when you...
1 second.
Okay. I'll give it a second.
Oh, there it is. Okay.
You have it?
Yep. Got it.
Okay. So we're all good then? Okay. So here's what we're going to do. I'm going to ask a question. I'm going to give you a few seconds to think about it. And then I'm going to say, okay, what's the answer? And you're all going to type in very quickly. In this case, it's multiple choice A or B. And that way I'll get an idea of whether or not everyone has, knows the answer, does not. Kind of like raising your hand in class or doing a multiple choice thing in class. That's a lot of fun, at least for me. So question, if we ask people to report their weight, would that variable be considered a categorical variable or a quantitative variable? So A for categorical, B for quantitative. I'm going to give you 5 seconds to think about it. Okay, there's no thinking that's required. Everyone's throwing out the answer, and I don't even think anyone said A. So that's great. Okay, that was very quick, and the answer is in fact that is quantitative. Okay, straightforward. We asked people whether their weight is underweight, normal, overweight, or obese. Is this variable categorical or quantitative? A for categorical, B okay, and there are all the answers without me waiting for okay. So, right. As questions get more difficult throughout the semester, and it takes time for some people to think about it, I'm going to ask not to throw in the answer until I say so that people can't see your answer and then to be influenced for how they want to respond. But for now, these are very quick. I think everyone, I do see a B here. So I do see a B. I see these Bs were from before because this is the first A. So underweight, normal, overweight, or obese, there's no numbers with those. Right, these are categories. Underweight category, normal category, overweight, or obese. It is a categorical variable. Does that make sense? Any questions on that? Okay. Okay. So now, next slide. When it comes to the distribution of the categorical variable, what we mean by the distribution of the categorical variable is very simple. We list all the categories, and then we list the counts or the percents, depending on which one is more appropriate for the problem at hand. We list either the count or the percent in that category. And as a visual display, we have two methods. These visual displays work for, categorical variables. They do not work for quantitative variables. Quantitative variables have their own display. These are for categorical. A pie chart and a bar graph. And hopefully you've seen these both. Let's go to the next slide for a pie chart. I would imagine everyone at some point in their life has seen a pie chart. If you haven't, you can message me privately because I'm just going to assume that everyone has. Because, I remember as a kid I did. So I just kind of assume that everyone else has as well. We'll go over it, but it'll be easier if we start off just being on the same page in terms of having seen it before. So if you look at the pie charts, first on the left side is a table. And it's a table of values for the question, what do the 1.5 million full-time first-year students plan to study? So a lot of people were asked 1.5 million, and we see 1, 2, 3, 4, 5, 6, 7, 8, 9. We see 10 different answers, and the percent of those 1.5 million that answered each of them. First thing I noticed is that the percents do not add to 100. Why do the percents not add to 100?
It says rounding error.
Yeah, so what does that mean, rounding error? What does that mean, a rounding error?
When you're looking at a percentage, it's not always going to be in the 100th decimal place. So when you round it up or down, it does affect the end percentage, which is 100.
That's exactly it, right? Those numbers, 13.9, 10.8, as I'm reading up the list, they're not exact. There are other decimals afterwards that we're rounding from, but when we add them all together, we're ignoring all those other decimals. And because of that, we might be off a little bit. Now, if you said 87.3 is your final answer, that's not rounding error. Okay, that's nowhere near 100%. All right, the most you can be off in any one of those is 0.1. Oh, I can do that as well. If I don't want people to be influenced by other people's answers, just ask everyone to privately message me in chat. That's a great idea. When you answer the question, do it privately. That way we don't, well, yeah, okay, let's try that. So next time I ask a question like that, rather than having it public, send it private. We'll see if that works. I can think of a reason why it should and shouldn't. We'll see how it goes. Anyways, now if you look at the pie, if you ignore the table for a second and just look at the pie, is it obvious which of those is the biggest slice?
Not really.
Not really. There's a few of them that are pretty close to each other. Right? Which are the three that are the biggest, or the two that are the biggest, or the five that are the biggest, whatever they are? Which ones might you think, if you didn't look at the table on the left, which of those would you think might be the biggest?
The orange
Biological
one.
sciences.
Sorry, say it again.
The orange one.
So the orange one is certainly amongst the largest. The one beneath it, which is gray, I guess, is pretty close, but a little less. The blue on the bottom is a little less. The brown on the top is a little less, right? It's close. And it's hard to trust your eyes sometimes, because sometimes it's hard to distinguish size like that, which is why we have the table on the left to be certain. Which of those categories is the largest on the left? Which is the highest percent?
Biological sciences.
Biological sciences at 14.9%. So what portion of the pie is going to be assigned to biological sciences? What percent of the pie are we going to make for biological sciences?
14.9% of the pie.
Yeah, 14.9% of the pie, right? The actual percentage is going to be the percent of the pie that we use, right? It seems very straightforward to do that, correct? Okay. It's very difficult to make a pie chart by hand. How exactly do you do a 14.9% slice? It's very difficult. Pie charts are done by computer. Okay, we do not do them by hand. You can get an approximate pie chart by hand, but you can't get a real pie chart by hand. In any project that you do in the course of your lifetime, do not do pie charts by hand. Okay, they're not going to be accurate. All right, the next slide, the other method of describing a categorical variable is via a bar graph. Be aware that a bar graph does absolutely nothing different than a pie chart. It just displays it in a different way. We have the same table on the left, the same percentages, but instead of using a pie chart, we use a bar graph where the percentages are given by the heights of the bars. Notice that the bars are all the same width. They're all the same color. They're separated by the same gap size. And the heights correspond to percentages. So if 1% is 20%, another is 10%, what would be the relation between those heights if one is 20% and one is 10%?
The 20% will be higher than the 10%?
Can you be more specific by higher?
10% larger.
How much?
The 20% bar is 10% larger than the 10% bar?
It is
twice as large?
Twice as tall. That's the idea. If 20% is twice as high as 10%, and 10% is twice as high as 5%, which is 5 times as high as 1%, and so on. So we want to scale them appropriately based on their percentages. Do you agree? Does that make sense? So again, some people like to, when they make their bar graph, highest to lowest, and others, like this one here, is alphabetical maybe, except for others at the end. That's really a personal choice. There's no hard and fast rule for how you make a bar graph. Just like there's no hard and fast rule for the pie chart, right? For the pie charts, it wasn't largest and the next to it second largest and the next to it third largest, right? It was just wherever they fell, correct? Right? There's no hard and fast rule. If you want to do it by size, you're more than welcome to if you think it's appropriate for the project at hand. Okay, does that make sense? So question, next slide. And we'll try to do this one with private messages. So that way I can see everyone's answers and get the general idea without one person being wrong and being embarrassed or anything like that. The purpose of pie charts and bar charts or bar graphs is to A, hide the data from the, oh crap. Nobody saw that, right? Good, nobody's smiling. Oh, people are smiling, so they did see it. Okay, whatever. A, hide the data from the audience. B, impress the audience with interesting colors and shapes. C, help the audience grasp the distribution of the data quickly. Or D, display the distribution of quantitative variables. So all these answers, yes, the answers on the, oh, so you're all seeing the same slide that I am, so you can, okay, that's a good point. Okay, you don't need me to slide down, you can just see it yourself. Okay, so quiet. So in the future, let's try to, be very careful as we go down. Oh, thank you so much. Thank you for blessing me. Let's try to be careful as we go down so that we don't reveal the answers too early because we want to make sure that we learn. I do see in these answers, some people are writing D. I do see that some people are writing D. Remember, pie charts and bar graphs are specifically for categorical variables and never for quantitative variables. Quantitative variables have their own method of display. This is for categorical and categorical only. Okay, it's not to impress the audience with interesting colors and shapes or to hide data from the audience. We don't want to hide anything, but we want you to grasp what's going on quickly without looking at a table of numbers. Does that make sense? The correct answer is C. So, and the next one is just another slide with the same answer. So that was done. Okay, so the next one, again, be very careful. Scroll down slowly so you don't accidentally or on purpose see the answer. It says married respondents in a survey were asked how they met their spouses. According to the bar chart below, approximately how many respondents met their spouses through, and of course, the bar chart is, I mean, the question is cut off. So I'm gonna, because I've already read ahead, I know what the question is, but you shouldn't read ahead. It's how many met their respondents through date service. A, 2, B, 20, C, 30, or D, 70. So this is fairly, let's see, everyone's giving me the correct answer. Excellent. Some people sent to me the answer to be 30, which while correct is also incorrect in the sense that it's a multiple choice question, A, B, C, or D. And while it is true that C is 30, the correct answer is in fact C, not 30, but nevertheless, 30 is C equals 30, someone wrote. Fantastic, C equals 30, even better. So that was pretty simple for that one. We can scroll down, and now let's go to the table for, to the slide for quantitative data. So the distribution of a quantitative variable tells us what values the variable takes and how often it takes those values. For the categorical, it was how often it fell into each category. And for quantitative, it's the values that it takes and how often it takes those values. Because remember, quantitative is numerical, whereas categorical are categories. So it's a slight difference in definition because it applies to a different thing. And we have two standard ways. Actually, there's a third that we might go over, we'll see. There's two standard ways of representing quantitative variables. The first one is a histogram, and the second one is a stem and leaf plots. Now, a histogram looks very similar to a bar graph, but there are differences. If we quickly scroll down a couple slides, we'll come back, but if we scroll down a couple slides, to slide number 26, we see a picture of a histogram. Just by looking at that histogram, what is one immediate difference between histograms and bar graphs? Yes.
The bars are touching.
The bars are touching. Okay, that's a humongous difference between a histogram and a bar graph. Now, is it possible in a histogram for bars not to touch?
Yes.
Yes, okay. If nothing fell in one of the slots, like for example, in that picture that we're looking at, if between 65 and 70 happen to have a count of 0, then the 65 to 70 slot would have nothing. Because it's a height of, you're putting a bar there if you think about it, but it's a bar of height 0. Okay, because the bars, one bar ends, the next bar immediately begins. Does that make sense? Any questions so far on what we're covering? So looking at this picture, the first of the bars goes from what number to what number? The first bar covers what number to what number? And that,
Go to
60 to 65.
so it covers 60 to 65.
Oh.
Right? The first bar is 60 to 65, correct? And the second bar is what number to what number?
65 to 70.
65 to 70. So if I got exactly a 65, which bar would I put it in?
The second bar,
Why the second bar?
because the first bar, it's less than 65.
Excellent, right? So the first bar says 60 to less than 65. That means the 64.999999999 and so on. And the second bar is 65 to not quite 70, so 69.9999999 and so on. So the bars can't have any overlap, but they have to meet, which means you have to be very specific for each one where it ends compared to the next one. Does that make sense? Yes, no, maybe so?
Yes.
Yes.
Okay. And what are the heights of the bars correspond to? So in this case, they correspond to the actual counts. So because one, whatever we're talking about, because one fell in between 60 to 65, the height of that bar is a height of 1. Next height, 1. Next height, 5, 9, 11, 23, and 1, and so on. Does that make sense? Now, the first one between 60 and 65, how many fell in that category? Oh, sorry, not category, I'm sorry. How many fell in that bar between 60 and 65?
1.
1.
1. What was its actual value? Trick question. We don't know. That information is not displayed in the histogram. We know that something fell between 60 and 65, but we just don't know what. That's one of the drawbacks of a histogram, is that while you know how many fell in each little slice, in each class they're called, you do not know their actual values. The stem and leaf plot, which we're going to look at in a few minutes, rectifies that situation. The stem and leaf plot also kind of has a histogramish shape, but it's a situation where we do not lose that information, but we're not quite there yet. So let's go back up to the previous slide. And let's look at these 5 bullets about histograms. Now that we have this histogram that we've seen, let's take a look at these 5 bullets. Bullet number 1. It's appropriate for quantitative variables that take many values and have large data sets. You don't tend to use this if you have 3 values. There's no need to have this visual display as a summary if the number of values is low. So we tend to use histograms for large sets of data. How large is large? Well, the example on the next page is 51, so it's not really large, but it's large enough. Bullet 2, we divide the possible values into classes of equal width. In our example on the next slide, what was that equal width? What was the width of each class?
5
5.
or 4.99999.
Technically 5, because the low, well, let's not argue about that one. Approximately 5. We agree? Approximately 5. Then you count how many observations fall into each interval. You can even have it as a percentage, 4% on this one, 12% on this one, 3% on that one, 18%, and so on. And then you draw a picture that represents the distribution, and the heights correspond to the values that you've calculated. So this particular example on the next page, freshman graduation rate, FGR, for the years 2013 to 2014. It's the freshman graduation rate, and on the left is the number of states. So how many states fell in the first class from 60 to 65? How many states had a freshman graduation rate of 60 to 65%?
1.
1 state. How many states had a freshman graduation rate between 65 and 70%?
1.
1.
1.
State, and so on. If you add up all of the columns, if you add up all of the counts, how many were there?
2.
Well, it can't be 2. We have 2 so far. There's a lot of other columns that I haven't included yet. I'm talking about if I add them all together, how many do I have?
8.
How many?
8.
50.
Oh, a lot more than 8.
50.
It's not 50.
51.
51.
51. But last time I checked, there's only 50 states in America. So what's the 51st? This is more of a sociology or a geography question, I guess, than a math question. But if there's
Are
only,
they referring to Puerto Rico?
I don't think they're referring to Puerto Rico. I think they're referring to the District of Columbia. But I got to be honest, I don't know. Because there are other American territories. But I'm pretty sure they mean DC. But that's not something that I ask. It's recognizing the fact that there are people who live, there are Americans who do not live in the 50 states. But I don't know, to be honest, which one it is. I think it's DC. Does that make sense? So just be very careful when I ask for the count. I'm not listening for how many classes there are. It's not 1, 2, 3, 4, 5, 6, 7, 8. Oh, the count is 8. Because you can have multiple counts in each class. You have to add up the heights. That gives you the total amount. Agreed? Questions? Make sense so far?
Makes sense so far.
Okay. So let's look at the next slide. Now we're on slide number 27. Examining a histogram. So you have a histogram and you want to conclude and you want to think about what's going on, right? In any graph of data, you're looking for the overall pattern, and you're also looking for striking deviations from that pattern. So let's scroll back up to the previous slide. If I had to give that a pattern, I'm going to give you 3 possibilities. Possibility number 1 is it's symmetric. I haven't technically defined these yet, so if you're not sure what they mean, don't worry about it. But possibility number 1 is it's symmetric. 2, it's skewed to the left. Or 3, it's skewed to the right. If you haven't,
To the right.
okay. So
Sorry.
someone says it's skewed to the right. Anyone else have another answer?
I think it's skewed to the left.
Skewed to the left. Does anyone think it's symmetric? Of course, to answer a question like that, we'd have to know what it means to be symmetric. A symmetric distribution is one that if you look at the center of it, it kind of looks like a mirror image on each side. It's symmetric. It's balanced. Okay. Does this distribution look balanced? If you look directly at the center, does it look the same on both sides?
No.
No, it's not symmetric. The question then becomes, is it skewed to the left or is it skewed to the right? Now, I have 2 private messages. One says skewed right, one says skewed left. So only one of them could be right, but they both could be thinking correctly. It's how you define skewed left or skewed right. The skewness is where the tail is. So if the hump's on the right and it tails off to the left, we would call it a skewed left distribution. If the hump's on the left and its tails off to the right, we would then call it a skewed right distribution. So now that we have that definition under our belts, what is this? Is this skewed left or skewed right?
Right skewed.
It's left skewed. The tail is on the left side of the graph. Right, the hump's on the right, and then it tails to the left. We're looking at the same one, right? On
Hump
slide.
meaning like the biggest one? Like the biggest bar thing?
No, the biggest bar, we're calling that the hump.
Okay, yeah, that's what I was thinking.
On the right, and then a big tail on the left.
Okay, that makes sense. Thank you.
So when we say it's skewed left, because the tail is on the left. Does that make sense? Now, just be aware, there are times that your eyes deceive you, and you think it's scaled skewed one way when it's really skewed the other way. There is a mathematical way of calculating skewness. And sometimes the math gives you an answer which is counterintuitive to what you expect just by your looking at the graph, because if you make histograms with different classes or class sizes, then different shapes can arise, and therefore it is somewhat subjective. So you have your guesstimates based upon the shape that you're looking at, but if you have an actual formula which calculates the skewness, whether it's negative or positive to the left or to the right, so one second, when you're looking at the questions about the 50 states, no, I asked my own question here. We're on slide 26. Ryan, do you have the PDF? Are you looking at the PDF with us? Yes, so we're on slide 26. Okay, so when push comes to shove, you always want to use real math, a formula to calculate something. This just gives us a general idea based upon what we see. Does that seem reasonable? Questions on that? Comments, allegories, metaphors, similes?
Professor?
Yeah, 1 second. So just to clarify, skewed side, meaning the side the tail is. Yes, so because in this case, the tail is on the left side of the distribution, I call it a left skewed distribution. Does that make sense? All right, got it. Sorry, what was your question?
That answered my question.
Even better. See, one person asked, more than one person has it. I love it. Okay, so let's go to the next. Sorry, so we're back to this examining histograms. We looked for the overall pattern, and we saw that we had a left skewed distribution. Were there any striking deviations from that? Was there any data that we had that says, well, that just doesn't fit? Remember, it has to be striking. Don't just make something up. It has to be striking. It has to be something that you see and say, whoa, where did that come from?
Would it be the 23 from 85 to 90?
I don't know. I mean, we have this shape, this left symmetric shape. Nothing wrong with a left skewed shape, right? If I had a big hump on the other side on the far left, then I might say, wait, why left skewed is a tail? Where is there a hump on the left side? I don't see anything here that makes it a striking deviation from the pattern, right? A left skewed is up and tail. And that's what I have here. So don't try to invent things that aren't there. Okay, if it's striking, you'd be like, oh, where did that come from? If you're not saying that, it's probably not there. And as we go on through the course and learn different techniques, you're going to see many examples of deviations from the norm. And we're going to even have a word for that. They're called outliers, things that just lie outside of the standard data. Does that make sense so far? Any questions?
Professor?
Yes.
When you say the tail, you don't mean what comes before the hump or what comes after?
So the tail is on the right side of the graph, right? Sorry, I apologize. The hump's on the right side of the graph, right? You have this big hump, right?
Yeah, it's on the
And
right.
then it tails off to the left.
Oh, like literally at the end. Okay.
Yeah, the long side is the tail.
Oh, wait.
Because if that tail wasn't there, it would be symmetric. Right? If that tail wasn't there, it's just a nice hump.
So anything that's before the like 80 to 85, that would be the tail?
Well, in this case, yeah, 60 to 75 or so.
Okay.
Again, we're not specific to the point of where does a tail begin? It's just an overall impression that we have by looking at the graph, right? There's a tail on the left side. It just keeps going. Okay. So next, you can describe the overall pattern by its shape, by its center, and by its variability. So the shape we've already talked about. The 85 to 95 is not part of the tail. No, the 85 to 95 is definitely on the other side. No, 100% not. Yeah, it's the numbers on the far left. Exactly. The tail is the low, long side of the graph. Okay, the right side, it might be low, but it's not long. It's not a tail on that side. It's just a little bit. That's not a tail. Tail is long tail. Make sense? So when we talk about the graph, we talk about its shape. The shape is one of three things in this course: symmetric, left skewed, or right skewed. That's the shape of the distribution. It's either symmetric, skewed to the left, or skewed to the right. You could say it's slightly skewed, or it's strongly skewed, or it's perfectly symmetric, or it's approximately symmetric. You can always throw in some adjectives if you'd like, but essentially we have three shapes: symmetric, left skewed, and right skewed. We could talk about the center of the graph, and we're going to hold off on that for now because it's a mathematical way of calculating the center. Essentially, the center is the middle of the graph. But what does that mean, the middle of the graph, when there's a tail? It's harder to determine. We're going to have a mathematical way of doing that, so let's ignore that for now. And we also have something called the variability. The variability of a graph is how much it varies. Is it really widespread, or is it very sharp? And again, we will have numbers to associate with those and formulas to use. We don't have to worry about guessing. We're going to have very specific formulas to give us the center and the variability. Shape, on the other hand, we're not going to have a formula for. That's just your overall impression of the graph. And you will sometimes see variability referred to as the spread. How spread out is the data? Is it from 0 to 100 or from 51 to 52? How spread out is the data? Okay, what is the variability? And an important kind of deviation is an outlier. An outlier is an individual that falls outside the overall pattern. If I asked 1 million people to pick a number between 1 and 10 at random, and it was pretty flat: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 7 would be an outlier because it falls outside of the pattern. Why would 7 be an outlier? Because everyone's favorite number is 7. Not everyone, but I'm just curious. Who here would have picked 7? Send me a message if you would have picked 7. I want to count how many that would be. If I said pick a number from 1 to 10, who here would have picked 7? Okay, well, I got one answer. I got 1, 2, 3, 4. My immediate thought was 7, 4, 5. So there's like 40 people in the class. I'm more of a 2 guy. Okay, sorry. You know, everyone's different. 7's a good movie. Yes, it is. If you haven't seen it, I highly recommend it. Just don't look in the box. And so you have a bunch of, no, you can have more than one answer that's an outlier. Maybe lots of 2s and lots of 7s and everything else is pretty even. You can have more than one outlier. The point is that sometimes you have just an answer that doesn't fit with the rest. Here's an example. Oh, I have one. Here's a great one. Suppose I went to a big hospital with lots of people giving birth, and I take data on what day of the week each mother gave birth. So it's a categorical variable, Sunday through Saturday, and I'm counting how many births there were in each one of the categories. What do you expect to see? Do you expect it to see flat, with the same number in each, approximately, which would be symmetric? Or would there be some kind of outlier in that situation that some days of the week might be more than others? What do you expect? Would you expect it to be pretty much even across the board because nature waits on no woman? Or would some days be different than others? So I see a bunch of people saying even. Okay, a bunch of people saying even, but I have someone say there will be an outlier. So that person who said there's an outlier, why would some days be different? Right? A lot of people were saying it's the same, but some people were saying, because it's random, it's true it's random. And if I only looked at 50 people, then yes, I might see some anomalies. But if I looked at 1 million people, then I would expect to have whatever the real distribution would look like. So some days are more stressful than others, which may, yeah, but people, if some days are more stressful, that should apply for everyone. You know, people can get stressed any day of the week. But people are not taking into account one important thing. Babies are delivered by doctors, correct? Doctors don't like to work on weekends. So if you're going to induce labor, which happens quite often, are you going to induce it on a Saturday or a Sunday? I mean, emergencies happen, of course, but chances are Friday through Sunday, you're going to have less births than Monday through Thursday. Weekdays should be more. Now, that's a hypothesis, right? That's a guess. You can always actually do a project. You can go to a hospital and say, hey, I'm taking a statistics class in college, and my hypothesis is that there should be either the same every day of the week, or I'm trying to calculate data. Maybe they'll even give it to you. They're not going to release names or anything like that, but perhaps they will. In that case, the outliers would be Saturday and Sunday, because those would be a lot less than the other days of the week, which would be pretty even. Or maybe Friday through Sunday, a lot less than the rest. It's just an example that I'm thinking off the top of my head. Okay, you can certainly, you know, try to come up with your own situation in which there might be an outlier. That was a good example. Thank you. Oh my God, that's so sweet. Here's another one. This is more advanced, but I'm sure people are familiar with the number pi. 3.1415 dot, 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 dot. Right, you guys are familiar with that. I'm sure you've seen it sometime in your life, the number pi. You know, I'm not saying see it like, oh, there it is, but you know, you've calculated it or you've seen it used in examples, you know, area of a circle, that kind of thing. So hopefully you all know this, but perhaps you don't. Pi is what we call an irrational number. That means it goes on forever and it never repeats. Okay, so there's no pattern. Numbers just keep coming by and they never just repeat themselves like a whole chunk pattern over and over and over again. So a question that mathematicians ask and work on, cutting edge research, is how many times each number appears in the decimal expansion of pi. So for example, we have a 3. So I'll make categories. Here's my 3 category. It's a tick mark for 3. Oh, next number is a 1. I'll put a 1 down. Then a 4. I'll put a 4 down. Here's another 1, 3.141. Now there's a 5. So the question that they ask is each number equally represented in the long term? And if not, why not? Now, I don't know the answer to this question. I'm pretty sure it's symmetric, but maybe it's not. I don't know. You know, and what do I know? I just teach, you know, basic math, statistics, and, you know, undergraduate math. That's what I mean by basic, not trivial math necessarily, but we're talking about cutting edge research. Pi does not take weekends off. That's right. Okay, pi goes every day. It never stops working. So when someone says, I would say yes, because it will be an infinite number. That's true, but here's an infinite number. Ready? 0.12121212121212 forever. That's infinite. And 1 and 2 equal, and nothing else occurs. So just because something is infinite does not mean that there's patterns in it. But maybe there are. I don't know. Let's move on. As just an example. Yes.
I was curious, in that case, if 1, 2, and are basically equal and they're highest, would they be considered the outliers in something that's 1 through 10 and you only have 1 and 2 and the rest is 0?
Well, that's a great question, because I don't know. That's a really great question, because if they're the outliers, then you're basically saying the normal is not to appear at all. And you know, things obviously have to appear if it's a number. So I don't know. That's a really great question. I I guess in hindsight, I probably could have picked an easier example, but I don't know. It's really a good question. I can tell you this, on any test question, it's not going to be something that's difficult to ascertain if you understand the concepts. That I can tell you. Okay. Class started at what time again? 4? No. What time did we start?
4.
4. So it's been 45 minutes. We got to be about halfway through class, right? Give or take. So let's take a 5-minute break. Let's come back in 5 minutes and we'll continue. Is that okay? I hope so. Oh, I'm tired. I want to go to sleep. Oh. All right, it's been about 5 minutes, right? Is that accurate? I don't want to start earlier than I said I would, so I'll give another minute or two just in case. Okay. I think it's enough time. So we're back. Okay. So let's look at the next slide, which is describing distributions. So we already talked about this a little bit. A distribution is symmetric if the right and left sides of the graph are approximately mirror images of each other. It's skewed to the right or right skewed if the right side of the graph is much longer than the left side, if the tail is on the right side, and it's skewed to the left if the tail is on the left side. We already spoke about that, right? Are there any questions remaining on right skewness, left skewness versus symmetric? So question, don't scroll down too much. We don't want to look at the answer. Look at the following histogram of salaries of baseball players. What shape would you say the data take? Take? Yeah, take. I guess data is plural. So what shape would you say the data take? Don't answer yet, because hold on. People are already answering, but okay. I guess it's kind of obvious. But is it? Because A says bimodal, and we really haven't described exactly what bimodal means. So can anyone tell me what bimodal means? Or just guess, maybe you'll be wrong. You go for it.
When the graph has like two peaks.
Yeah, exactly. Not two skews, someone texted me, but two peaks, right? So if it peaks once and then it peaks again, and those two are roughly the same height, we would call it bimodal. We don't have that here. So we have bimodal, left skewed, right skewed, symmetric, or uniform. Uniform means it's the same height across the board. So someone said B, which is left skewed, but remember the tail is on which side? The tail is on the right side, which means this is right skewed, which most people did say C. So that's great. Again, next slide, don't scroll down too much. It says, look at the following histogram of, oh wait, this is the same thing. Never mind, that's just the answer. So, okay, next slide is a new question. It says, look at the following histogram of percent urban population in the 50 US states. So don't scroll down too much. Don't look at the answer. So we have bimodal, left skewed, right skewed, symmetric, or uniform. And the question is, what shape would you say the data takes? Okay, so looking at these answers, I see a lot of A's, a lot of B's, a C. Okay, so I don't see anyone say D, symmetric, which is great because it's certainly not a mirror image on both sides. I don't see anyone saying E, uniform, which is great because it's not the same height everywhere. Okay, oh, someone did say E, I'm sorry. But it's not E. Uniform means the same height everywhere, and this is certainly not the same height everywhere, right? It's low, goes up, peak, back down, peak, back down. So this is certainly not uniform. The question is it left skewed or right skewed? Well, the tail is on the left, so it's certainly not right skewed. So I don't think anyone said C, which is good. But the question is it A or B? A says bimodal and B says left skewed. So there's certainly a tail on the left, but there's also two peaks. So this is one of those questions that I would never ask on a test because both answers are really legitimate answers. And in fact, I think both of them are correct. I didn't make this PowerPoint, it's from the department, but I would say both of them are correct. It's both left skewed and it's bimodal, nothing wrong with that. Their answer is left skewed, but I would have given credit for bimodal as well. So either
I have a question.
Yeah, go ahead.
For bimodal, does that mean that the two peaks have to be the same height, or is just two peaks in general?
They should be the same height or at least very close to each other.
Okay.
Okay, because the mode is the one or ones that occur the most times. So if I have like this, it's pretty low, peak, peak. This one this peak dominates the other peak. So if one peak is so much bigger than the other, then that's the mode. But if both peaks are roughly the same, it's bimodal.
Okay, thank you.
You're welcome. So let's go to the next question. Again, don't go
I have
too
a question as well.
Yes.
And for the peaks, it doesn't matter where on the graph or on the chart they are, as long as they are not symmetrical, right?
Say it again, please. I'm sorry. I missed
I
it.
was saying that for the peaks, it doesn't matter where in the graph they are, as long as it doesn't look symmetrical.
You're talking about
Bimodal?
for bimodal, no, it could be symmetric and bimodal at the same time. If I have a graph that looks like this, can you guys see my board? If I have a graph that looks like this, can you see that?
Yeah.
So that's symmetric, right? If you look at the mirror, you look at the center line, it's the same on both sides, but it's also bimodal, right? It also has two modes, so it can be both. That's why the previous answer is technically both of them are correct. Does that make sense? Yes, no, maybe so? A little bit, possibly?
Yes, it makes sense.
Oh,
Yes.
I got a thumbs up. Fantastic. Okay. So next question. Excuse me. Next slide. Again, don't go too much. But the next slide says, wine bottles at a small winery are sampled and tested for quality. One measurement is volume. The bottles should be filled to 750 milliliters. But of course, some variation is expected. So look at this histogram. Does it seem reasonable that they're about 750 milliliters? Right? If I was this manufacturer and I was trying to make sure that my wine didn't have too much or didn't have too little, would I say that essentially on the average, I have 750 milliliters per bottle? Yes, right? The center of my graph, and it's fairly symmetric, the center of my graph is right on 750, correct? And it's a very symmetric looking graph. Agreed? It's not a perfectly symmetric, but very symmetric looking graph, right?
Yeah.
Okay. So A, B, or C? Yes, the center is approximately 750. B, the center is too variable. Or C, the data range from 740, okay, so the answers, so the question is, does 750 seem to be a pretty good center? And there's three answers, A, B, or C. So go ahead and read them, and then shoot me what you believe the answer is. So I see lots of the same letter, and actually I think everyone had the same letter, which is fantastic. The center is approximately 750, and even though there's a little spread, that doesn't change the fact that the center is 750, right? So that's great. Next one, and I think everyone answered A. I didn't see anyone say not A, so that's wonderful. Oh, I did see a B. I did see a B. The center is too variable. No, the center is not too variable. The center is pretty much exactly 750, right? It's right in the middle of my graph with symmetry on both sides, correct? Right? I hope so. Okay. Next question. Considering this histogram, how many bottles of wine have more than 752 milliliters? (17) A, B, C, or D, essentially. So I'm looking for answers. I don't have everyone saying the same answers, so I'm going to wait till I have a few more. Oh, I have lots of answers all over the place. I have A's, I have C's, I have D's. I don't think I have any B's, but I have A's, C's, and D's. So more than 752. Well, let's take a look. Look at the first class that is after 752? First of all, how many classes are there after 752 in this picture? There's 2 classes. There's 752 to 754, and there's 754 to 756, correct? What's the count for the 752 to 754 class?
5.
5.
5. And what's the one for the other one?
1.
1.
For a total of?
6.
6.
That's the count, 6. Right? That's the count. Okay, moving on, next slide. Okay, next question. What 3 features can best describe the overall pattern of a histogram? Take a few minutes and think about this. A, B, C, or D? Shape, center, and skewness. Center, spread, and outliers. Central, mean, and symmetry. Or shape, center, and spread. Which ones describe the overall pattern? So let's take a look at what I have here. I have different answers. Actually, I have all 4 answers amongst everyone. So everyone is well represented here. I have A's, I have B's, I have C's, and I have D's. And I have the most D's, which is correct. If you go back a few slides, shape, center, spread are the 3 basic features of a histogram. Shape, center, spread. Yes. How do we describe the shape? We use the term skewness. And we did speak about outliers. There's no question about it, 100%. But nevertheless, when it comes to straight up the 3 essential features, they are shape, center, and spread. Because skewness, someone said, why not skewness? Skewness is not its own concept. Skewness describes the shape. Okay, it could be either symmetric or it could be skewed. That's the shape. Does that make sense? Yes, no, maybe so? Anyone?
Yes.
Okay, well, I'm talking specifically. I wouldn't say skewness and shape are the same thing. Skewness is one of the possibilities for shape. When you talk about shape, it's like, what kind of shape does it have? Oh, it's skewed. So it's not the same thing, but it's a possibility. Got it. Excellent. Okay. So next one. Oh, that's just the answer. Okay, next one. Which, and that's the same answer again. Okay. So now we're on slide, it looks like we're on slide 40. Moving right along. What time's class over anyways? We got time, right? We're not running out of time. 4 to 5:40. Okay, we got plenty of time, right? Who wants to leave early? We don't want to leave early. We're doing math, right? This is great stuff, isn't it? Okay. So an individual value that falls outside the overall pattern is called what? A, the center, B, the shape, C, an outlier, or D, a spread. And if you look at that pattern, what do you see? What do you see in that pattern? Would you say that there's an outlier in that pattern?
Yeah.
Yes. In fact, there's a big black arrow pointing right at it. You have the basic shape, and then there's a gap, and then there's something off to the side. So what do we call it? A, B, C, or D? I think everyone, I hope everyone else, some people did say D. Do I have anything for A or B? No. I have C, and then I have lots of D's. I mean, lots of C's and a D. Remember, D is a spread. D is how wide it is, correct? But an outlier is specifically the value that falls outside of the pattern. So the answer is C. So that takes us to the end of histograms. Are there any questions on histograms before we move through? Because next we're going to talk about stem plots, which is the other method of describing a quantitative variable. So are there any questions up until now? Okay. Would this graph be symmetric in shape? Anthony, when you say this graph, can you be more specific? I'm not sure what you're referring to.
On slide 40. Like if you're asking us about the shape of this graph, would this technically be symmetric?
For 40?
Yeah. Or
No, I would still call it right skewed because even though
Okay.
there is an outlier, it's still part of the tail.
Gotcha. Okay. Thanks.
But again, no problem. But again, remember that sometimes the way we see things isn't always mathematically the way it actually is, right? So I might guess that it's right skewed, and then do the math, and it turns out that it's really not. Okay?
All right.
All right. Anywho, so stem and leaf plots. To make a stem plot, it says separate each observation into a stem consisting of all but the final or rightmost digits, and a leaf, the final digits. So like 842, the stem would be 884 or 84, and the leaf would be 2. Okay, again, we haven't really gone to the gist of this yet, but first step, you have all your data, you separate them into stems, all the digits but the last one, and the leaf. Does that make sense so far?
Yep.
Oh, I hope. Okay. Then stems may have as many digits as needed, but each leaf can only have a single digit. Leaves cannot have more than one digit. They can only have one. Sorry, I talk a lot, so I gotta have some of my vodka every day. All right, that's step 1. Step 2, write the stems in a vertical column with the smallest at the top and draw a vertical line at the right of this column. And it's very important to include all the stems needed to span the data, even when some stems have no leaves. Again, we'll see one in a second. And this very abstract definition and approach will make a lot more sense. And then it says, write each leaf in the row to the right of its stem in increasing order out from the stem. So let's look at an example on the next page. Unless you need a second to write any of that down, I'll give you a second to write it down. Okay, so let's look at it. On the left side, you have 3 columns of data. This is weight data for an introductory statistics class. One person weighed 192, one person weighed 152, 135, 110, all the way through 106. Notice that each of the pieces of data contains 3 numbers, and each one specifically ends in the units place. So there's no like 110.4 or something like that, correct? They're all 3 digits and they all end in the same location. So if you look at the first one, 192, the 1 and the 9 would be the stem, and the 2 would be the leaf. For the next one, the 15, the 1 and the 5 would be the stem, and the 2 would be the leaf. Does that make sense so far? And what you do, if you look at the blue big box on the right, they're starting their stem and leaf plot. What they do is they start with a stem of 10. Why do they start with a stem of 10? Because the lowest number in your data is 100 something. And because it's 100 something, the lowest stem that we would ever have is a 10. What is the highest weight in your data? 260 something, correct? So the last stem would be 26. And then we include everything in between, whether or not there's data for it, 11, 12, 13, 14, 15, all the way through 25. And then after the stems, we write the leaves. So notice that after the 1, 9, we put a 2. Why? Because we have 192 as part of our data. And after the 15, we put a 2. Why? Because we have 152. And then 135, so we have 1, 3, then 5. What would I write next if I was going to complete this chart? If I'm going in order, what am I writing next?
A 0 next to the 11.
A 0 next to the 11. And then?
An 8 next to the 12.
An 8 next to the 12. And eventually, I keep going, and I get to the very bottom of the first column, and I get to 150. When I get to 150, what am I going to put?
A 0 next to the 15.
A 0 next to the 15, but I already have a 2 next to the 15. So what I do is I kind of erase the 2 and put the 0 before it, and then put the 2 again. So it'll be 1, 5, vertical line, 0, 2. The leaves are just the last number. The first numbers are the same for the whole row. So 2 numbers for the first column, and is in this case, but if I have thousands, it might be 3 numbers for the stem and 1 number for the leaf.
So the last numbers you're recording go in the front, on the left side of the old numbers?
The leaf is the last number. I'm sorry, say that again, please. Yes, the leaf is the last number. What would you say? I apologize.
The further down the line you go, the newer leaves that pop up that are double in stems, you put it on the left side of the older numbers?
No, you put them in order from lowest to highest.
Oh, okay. So if the 15 was a 3, you'd put 2, 3?
Yes, exactly.
Okay.
Exactly. So usually when you put this data down, you don't go and order the data because then there's a lot of erasing and fixing. You kind of look through them and say, okay, which are the ones that go with 1, 0, this one, this one, and this one, and you put them down. And then you cross them out. And then which ones go with 1, 1? Oh, those 2. You put them in order, you cross it out. So you kind of don't just go on the data unless you want to. Then you just leave a little gaps, and sometimes you got to erase and rewrite, and it's part of the job of doing this correctly. Does that make sense, though? Yes, no? Anyone have a question on this technique? Okay. So let's look at the next one. If there are very few stems, in other words, the data covers a very small range, we may want to create more stems by splitting the original stems. An example, if all of the data was between 150 and 179, I might not want to only have a 15, 16, and 17. I might feel that that is clumping the data too much. I might want to create another collection of stems by using 15 twice, 16 twice, and 17 twice. The first 15 will be 0 to 4 as my leaf, and then 5 through 9 will be the next one. 16, 0 through 4, 5 through 9, and then 17, 0 through 4, 5 through 9. So I can double the stems and have possibly a different shape of the data, which I might feel explains things better. So in this example here, 0 to 4 goes in the first, and then 5 through 9, 0 to 4, 5 through 9, 0 to 4, 5 through 9. So let's look at the question on the next page. Again, don't go too far. In the data set represented by the following stem plot, in which the leaf unit equals 1.0. In other words, the last number here is a decimal. So for example, the first thing in the leaf plot is 0.9. What number is that 0.9 represented by? What is that? What is the actual number if I have a 0.9 for this example?
0.9.
0.9. And what is the next number in my data? after 0.9?
1.2.
1.2. And what is next?
1.4.
2.11.
1.4, right? 1.2, 1.4, 1.6, 1.9, 1.9, 1.9. You see how I use the same stem for 6 different leaves? Do you guys see that?
Yes.
Yeah.
I'm using the same stem for 3 different leaves. Sorry, for 6 different leaves. 1.2, 1.4, 1.6, 1.9, 1.9, 1.9. What comes next?
So it's kind of like you're doing the distributive property, except you're not actually like multiplying anything or just.
Yeah, in a sense, you're
Okay.
distributing it. That's right. It's not, I mean, I wouldn't
Okay.
call it that because it's not, but I see
Yeah.
why you're saying it. I definitely see why
Okay.
you're saying it. What comes after after the third 1.9, what comes next?
2.1,
Then,
2.1,
then,
2.1,
then,
2.1.
and so on.
Yeah.
Does that make sense, everyone?
Yeah.
So the question is, how many times does the number 28 occur? A, 0 times, B, once, C, 3 times, or D, 4 times? Go ahead and show me your answers.
Is it the
Wait, don't say the
28?
answers.
Or is it 2 and 8?
Yeah, it's 28, the number 28. How many times does the number 28 occur in this data? So the answers are pretty much split between A and C. And I don't see any B's or D's, which is good. And I can see why people would say A and C. One of them is right, one of them is wrong. So the answer is A. 28 does not occur at all. 2.8 occurs 3 times. Right? Remember, 2.8 occurs 3 times here. But 28 is too big for this data. 28 is way off the charts. What's the highest number in this data?
7.3.
7.3. 28 is nowhere close, right? 28 is not part of this data set. So it's very important when you have a stem and leaf plot that you understand which units place, which decimal place we're in, which is why on the vertical line, you see those little dots to indicate decimals. Now, I personally have never seen that before. I think it's very smart. I like it. But you should know from either from the context, in which case they specifically said the unit here is 1.0. That was part of the problem. The unit is 1.0. So does that make sense why the answer is A and not C? Is anyone still unclear on that one?
Professor, on the next slide, it said that the answer is C. Was it just maybe like a typo? Did they like meant to put like 2.8?
Well, it's very possible they did. I was answering the question that I read, which is how many times did the number 28 occur? The answer is 0. Their answer is wrong. Their answer is wrong, and I shall contact the PowerPoint authorities and let them know that they're what is poggers? That's like a term of your generation. So tell me, what's a pogger? LMAO, a lamois. Okay, so a pogger is a lamois. I got it. All right. I've learned so much. You guys teach me, I teach you. I think it's fair. Okay. Anyway, F for, I don't know. We'll keep going. Okay. Anyways, the correct answer is A, not C. That is a mistake on the PowerPoint. So if anyone just said C because the PowerPoint said C, let that be a lesson to you that they're going to make mistakes. And because they make mistakes, don't immediately assume they're correct.
I have a question.
Right. Yes.
So for every stem and leaf plot, there will always be a unit of measurement, right? That is like in the question. Like this one says leaf unit is equal to 1.0.
Yeah, so either it'll be in the question or it'll be determinable from the context of the question.
Okay.
Okay, but it has to be one or the other because without, you just can't answer it. Never assume. Yeah.
So the unit of measurement can't go over 9, right?
Well, the unit of measurement will always be a decimal. In other words, they're basically telling you which decimal place the last number, the leaf, falls under. Right? So it's either going to be 1.0 or or 1 or 10 or 100 or 1,000 or 1,000,000, whatever they are. It's really more of an order of magnitude so that you know what spot we're in the decimals. Does that make sense?
Thank you. Yeah.
All right, so next question. What is one advantage of histograms over stem plots? A, histograms can be created by hand. B, the data set can be any size. C, the actual data can be extracted from the histograms. Or D, histograms can be horizontal or vertical. So let's see what we got here. Okay. So I see 1 answer, 2 answers, 3 answers. A lot less for this one than some of the others, but people are still sending in answers. So I have B's, C's, and D's. I don't have a single A, which is great because they both can be done by hand. What's the advantage of having a histogram? Oh, I can do it by hand. You can do a stem and leaf plot by hand as well. That doesn't make any sense. If I look at B, the data set can be any size. Let's skip that for a second because that's the correct answer. C, the actual data can be extracted from histograms. So I already spoke about this. For a histogram, we have widths, we have classes, and we know the data is somewhere in there, but we don't know the actual data point. It's between 60 and 65. What is it? I don't know. 61, 2, 3, 4, 64.7. I have no idea. You cannot get that from the histogram. And D, it could be horizontal or vertical. Well, either of them can be. I can make a vertical stem and leaf plot if I wanted. I can just, instead of having the stems this way, I can do the stems this way and the leaves go up. I can do that if I wanted to. I'm not sure why I'd want to, but I could. But the answer is B. The data set can be any size. Because remember, for the stem and leaf plot, you have to write a number for each leaf. If I have 1,000,000 data points, you're going to write down 1,000,000 leaves. That's going to take a long time. But for a histogram, it's just a bar whose height represents how many fall in that class. You're making 1 bar for the entire class. That's not very time consuming in comparison. Does that make sense? Now, if I scroll down to the next one, what is one advantage of stem plots over histograms? So go ahead and read that, A, B, C, or D. What is one advantage of stem plots over histograms? So let's see what people are saying. I see, well, people are still reading probably, which is fine. All right, I see A's, I see B's, I see D, A, B's, and C's. I see a D, so we got across the gamut, we got everything. So let's take a look. What is one advantage of stem plots over histograms? A, stem plots can use classes of any size. No, stem plots cannot use classes of any size. They're pretty much determined by the number of digits. So if I have 3-digit numbers, they have to be 2 digits. We don't have any choice in that one. It's set. So that can't be. B, the data set could be any size. Well, we've already spoken about this. I'm not going to want to use stem plots for large data sets. It'll take forever. C, the actual data can be extracted from stem plots. This is the key. This is the advantage of stem plots over histograms. We actually can just read the stem and leaf off and we know the actual data. So I can always get back the actual data if I felt I had to. And horizontal or vertical, we've already spoken about that. It could be either one. So the answer is C. And most people did say C, which is nice. So that's the answer to that one. Okay, and then finally, we have the last idea in this section, which is a time plot. Now, a time plot is a different animal altogether than a categorical variable or a quantitative variable. A time plot measures one variable over and over and over and over again. So for example, if I go to the hospital and they hook me up to I think it's called an electrocardiogram, you know, the thing that goes like this, right? Any future doctors here who know what I'm talking about? You know, I watch Grey's Anatomy a lot, but they never say the word, so I'm not sure what it is, but you know, whatever that's called. EKG, so it is an EKG. The thing that beeps, that's the one. So what it's doing, it's measuring your heart thing, your heart rate, your heart rhythm, I don't know what it is, and it keeps measuring it over time. So it's measuring the same thing over and over and over again. So looking at the slide, a time plot shows behavior over time. Time is always on the horizontal axis, and the variable being measured is on the vertical axis. That's just independent variable, dependent variable. You're looking for an overall pattern, a trend, and you're also looking for deviations from the trend. Is it going up? Is it going down? Is it alternating? Is it maybe sinusoidal, like a sine curve or a cosine curve? We're looking for trends, and we're looking for deviations. And quite often what we do is we connect the data points by lines to emphasize the various trends that we can possibly see. Does that make sense so far? Yes, no?
Yeah.
Everything good?
Yes.
Yeah.
Okay, and you know, sometimes anyone here play a stock market? I personally don't, I've lost enough, but I have friends who do, and sometimes they'll show me these charts that they make with these trends, and he's got these things. It's crazy how much analysis goes into it, but of course they probably make a lot more money than I do, so maybe I'm the crazy one. But we're dealing with time plots. We're looking for things that change over time. If I know, for example, that a stock will go up every summer and goes down every winter, if I knew that, then what would I do? I'd buy it before the summer, I'd sell it at the end of the summer, and repeat every year, right? So you're looking for trends. You're looking for patterns, maybe seasonal variations. You know, maybe something that is used often in the winter, like firewood. I don't know if people do use firewood anymore, like oil or coal or something that heats the house, may be more expensive in the winter time when people are not here in Los Angeles, but you know, I'm from Chicago, so maybe a colder climate. I don't know. People are looking for these trends, and they'll analyze and they'll see if they exist, and if they do, they'll try to act accordingly. So here on the next slide, we have the class makeup on the first day, and the percent of the class that are freshmen. So I'm not sure if this is for Math 140 or not, or just from some hypothetical class. But what do we notice is the general trend over time?
It increases.
It seems to be going up over time. Okay, sure, there's always going to be some fluctuation. Nothing's ever perfect in real life, but it does seem to be increasing over time. The next one shows the average tuition and fees for public schools and private schools over time. What do you notice about both of these?
It keeps going up.
They're going up. Is one of them going up at a faster rate than the other?
Yeah.
Yeah.
Okay, so it's the comparison of the two, which sheds some light on the issue as well. We don't just have one time plot, we have two time plots. So the next slide. Well, oh my God, we got so much to do. These things are crazy. So 53. Which of these plots is a time plot? A, B, both, or neither? Which of them is a time plot? A, B, both, or neither? Go. Okay, so there's only two answers that I have so far. I have a lot of A's and a bunch of C's, no B's or D's, which is good. The answer is A, only plot A, because remember the first key of a time plot is the horizontal axis has to be time. What is the horizontal axis for the left plot?
Year.
And what is it for the right plot?
Net.
Yeah, well, net generation of electricity, that ain't time. Time plots have a horizontal axis of time. We're measuring the same thing over and over and over again. We're not measuring different things. So the answer is just plot A. Next slide. This is on number, don't slide too much because the answer is on the same slide, but we are now on slide 55. What type of trends is shown? Is it an upward trend, a downward trend? Sorry, downward, upward, or no trend? Downward, upward, or no trend. So this one hopefully is fairly obvious, and the answer is, everyone said the answer. The answer is upward B. That's correct. That was really straightforward. Slide 56. What would be the correct interpretation of the following graph? Upward, downward, or seasonal? Excellent. So I think everyone said the correct answer. It's seasonal, right? It goes up, it goes down. Oh, someone said A, upward trend, but this is certainly not upward. It goes down, up, down, up, down, up, down, up. This can't be an upward trend. Upward trend would be just be up. Maybe some fluctuation, but the overall trend would be up, and we certainly do not have that here. The answer is C. And I believe the last question, for data involving answers, what is the best method of displaying the data? How many times have you accessed the internet this week? A, sorry, 1, never. 2, once or twice. 3, 3 or more, 4 times. 3 or 4 times, or 4 more than 4 times. That's okay. So the answer A, B, C, or D. Do you want a bar graph, a box plot, a histogram, or a scatter plot? Okay, a bar graph, a box plot, a histogram, or a scatter plot. Well, so here's a good key. When you're asked a question that involves topics that you haven't learned yet, the answer is probably not going to be them. So we have not studied scatter plots, and we have not studied box plots, which means it's not going to be B or D because we don't even know what those two things mean. It's got to be either A or C, correct? And the question is, what are we measuring? A categorical variable or a quantitative variable? A categorical variable would use a bar graph, and a quantitative variable would use a histogram. And what type of variable do we have here? We have a categorical. They're numbers. They're numbers, but they're categories. How many fell in this category? How many fell in this category, in this category, or in this category? It is a categorical variable, and as such, we would want to use a bar graph. So this takes us to the end of both class today and the first PowerPoint. We finished the first chapter. The homework will hopefully be up by tomorrow at the latest, possibly even tonight if I can figure out the issues. And you will have a full week to do it. So from the second it goes up, I will then email the class saying homework is up, so that you know you will have 7 complete days to do it. And either way, we are starting chapter 2 next time, so make sure that you understand this material before we move on. Any questions?
For the last question you just did you say it was a histogram or it was a bar graph?
It's a bar graph because we're dealing with categorical data.
Okay.
Right? There are categories. How many fell in this category? This is actually really interesting. Oh, well, thank you. Oh my God. That's amazing. Poggers, or I'm not sure if that holds or not, but whatever. So anyways, that's it for today. Have a great weekend. Study. Go out. No, don't go out. Wait, pandemic. Stay in and study more because you have no excuse because you can't go out. So that's wonderful. And I will see you all on Tuesday. Yes. Okay. If I don't fix it, Hannah, just let me know. All right. So everyone have a great, I appreciate that. Thank you. Have a great time. I'll see you guys next week. Yes.
Professor?
Yes.
So I was looking on Sapling when I first bought it.
Yeah.
And it said the chapter 1 assignments were on the website already. I opened it to see what it was, and I attempted the first question, but if you haven't posted the homework, what did I do?
Well, it's possible that the math department already posted it for all classes.
I see.
So
Okay.
that is a possibility that I'm still trying to figure out because I was assigned this class relatively late in the process, and I had a lot of work this summer, and it's my own fault. I should manage my time better, but I'm not the best at that.
Gotcha.
I'll figure it out, and as soon as I know, I will let you know.
All right. Thank you very much.
You're very welcome. Anyone else have a question? Okay, then I will see you guys next week.
All right. Thank you.
You're welcome. And Dorian, I know I'm funny, but you laugh a little too much for class. What can I say? So just saying. And then there were 12.
Professor, I have a question.
Yes, go ahead.
Really random. If there's a conflict with any dates that you've put up with, like, to do with like quizzes and stuff, like let's say I have something really personal going on one day, would I inform you right now about it to work with you, or would that be inexcusable and I would have to figure out?
No, listen, I try to be accommodating as best I can.
Right.
So especially if it's private, you might want to just message me.
Yeah, okay, I was just making sure that that's it.
I'll try to work with you.
Okay, I'll email you soon. Thank you.
Gotcha. Anthony's, okay, that's good to know. So cool, so that's a good term then. Okay, gotcha. I did not know that. I knew that now, so I do appreciate that. Thank you for looking out for me, man. I do appreciate it. Power to the people. All right.
I have a question.
Yes.
So for the sapling thing,
yeah,
like I'm trying to register, but it's, I mean, I guess you wouldn't really be able to help me out because you don't like work with them. But
so
it's
I don't
not working when I.
Okay, well, give me till tomorrow. Tomorrow morning, I don't teach till I have off the whole morning until like 1 o'clock. So I'm gonna try to get everything straightened out in the morning, and then I'll send a message out to the entire class, and hopefully everything will be up and ready by then. Is that okay? Can you wait 12 hours or so? Or
oh, never mind. I think I got it.
You got it?
Yeah.
Okay. Okay.
Do we have to like add your class, right? Or is it already like?
You're not in my class. What do you mean?
Like when I sign in, am I like already part of your class, or do I have to?
Oh yeah, I gotta figure that out. I gotta figure that out. It's the first time I've worked with that particular software. So,
Yeah.
so as soon as I know, I will let you know.